Welcome back. Today we are going to do 6.2, which is interpreting graphs. And so basically this is going to be our focus for today. We're going to describe patterns found in graphs, extend graphs to determine unknown values, and estimate between values on the graph. So basically we're going to be given either a table of values or a graph like this, and we're going to learn how to read what that data means. It's pretty straightforward. First word that we have to learn is interpolate, which means estimate a value between two given values. And it should only be used when it makes sense to have values in between. So for example, we're going to have a graph, and let's say we have these points on the graph, and then the question will ask us something like, what is this value here, or this value between the points? And so we can sort of kind of estimate by looking at the different axes what that value is. Okay, so we're going to do a question like that first. So let's start with example 1 here. It says solve a problem using interpolation. So a weather balloon recorded air temperature at different altitudes. The data approximately represents a linear relationship. So in this particular section, you likely won't have to graph too much, but if you did, you would basically draw yourself a graph these values, and we'll talk about how to do that in the next section. But lots of these questions will actually show you the graph, which is on the next slide here. So we have 3 questions we have to do. Interpolate the approximate value for the air temperature when the balloon was at 600 meters. Then we have to find the altitude when the temperature was minus 7.5. And then part C we'll do after. So I'm just going to jump to this data. So here is what the data looks like, and it's graphed for you. So this is the temperature on what we call the y-axis, and the x-axis shows the altitude. Okay, so we've graphed the data, temperature versus altitude, and so we'll now look at part A. So it says interpolate the value for the air temperature when the balloon was at a height or altitude when the altitude is 600 meters. We want to know what the temperature was. Okay, so all we're going to do is look at this graph and find where is the altitude 600 meters. Well, you see they start us for us. So even though there's no point directly on 600 meters, we can sort of find where that point would be and then draw it as best we can over to the y-axis. So you see that red dotted line takes us over to the y-axis, and if we estimate, what does that look like? Well, it's right between 5 and 10, so we can say the temperature is about 7.5. And technically a better answer, let's scratch that, would actually be 8. So we can't estimate decimal points that easily, right? We know it's between 5 and 10. It looks like it's exactly between, I would accept 7, I would accept 8. Technically what I did here with the 7.5, we can't estimate that accurately, so we should round it to a whole number. So we'll say 8. All right, part B says, what was the approximate altitude of the balloon at an air temperature of negative 7.5? So now we're sort of reading it backwards. So we're going to look at the graph. So when the temperature is negative 7.5, so you see this blue line here. When the temperature is negative 7.5, they drew it all the way across, and then we guess this value. It looks like it's a little bit higher than 1700 or 1600. They said it's 1700. Again, they're trying not to get you to estimate too specifically, so what the question says, when the temperature is negative 7.5, the altitude they're saying is 1700. Okay, it's between those values. Even though we can see with our eyes it's not directly between it, because it's between, that's why they rounded it up. Okay, and again, in class we could go over some other examples more specifically how to round it, but try not to get frustrated if your rounding is a little bit different than the textbook. It's just supposed to be an estimate, okay? And then part C says, is it possible to interpolate the precise value for the air temperature when the altitude is 10,050.92 meters? Okay, and so the answer is no, because even though so 1,050, sorry, so that would be in here somewhere, but it's way too specific to get that value. Okay, so we can go on the lines, we can go between the lines, we can do our best estimate, but something that specific, it's not possible. Okay, let's try another one. It says the graph shows a plane's altitude as it lands. So obviously the altitude is going down as the plane lands. It's approximately linear, which means it's a straight line. Okay, if you graph something and it looks like this, okay, it's obviously not a straight line. So then you can't do any of the stuff we're doing. It's only for linear relations. So what was the plane's approximate altitude at 50 seconds? Okay, so let's see here. So time is on the bottom. So when time is at 50 seconds, okay, we see this dot. Oh, sorry. So when time is at 50 seconds, it's between 40 and 60, right? So it's right here somewhere. So right here, we have to ask ourselves, what is this value if we look to this axis? Okay, well, it's about 10. Okay, so when t is 50 seconds, we can interpolate by going between the dots, and we figure out that the altitude is about 10 kilometers. Okay, part B says, at what time was the plane's altitude approximately 11 kilometers? So we look here, 11 kilometers. So 11 is going to be, somewhere between these two. So we'll go across somewhere here, and I'll say, it's approximately 40. Okay, so when the altitude is 11 kilometers, the time is about 40 seconds. All right, so we'll leave that one there. Extrapolate is the other thing we're going to talk about today, and that means estimating a value beyond a set of given values. So if we have a graph, we have some points, it goes up to here. Extrapolation is basically saying, where would the graph be this time? So we're kind of extending the graph, and we're doing the same idea. We're going to kind of guess what it would look like if we extend it either there or even the other way. And just like the last one, it should only be used when it makes sense to have values beyond given values. So there's some examples where you can't really go beyond a graph, and you'll see what that means. So if it makes sense to go up or down, but otherwise it's the same idea. So the value of a computer decreases over time. Here's our first example. The graph shows the value of a computer after it was bought. So obviously when you buy a computer and try and sell it 3 years later, you can't make back what you purchased it for, right? That's what this graph is showing. So after what approximate period of time does the computer have no value? Okay, so when is the value 0? So we're trying to find for part A, when the value is 0, how long does that take? So it might be a little tough for me to do here, but what you're supposed to do is extend this graph, use a ruler if you can, dotted line, and it should be straight. I have for my stylus here, so if we extend this line as best we can, okay, I'll let you do it better, we get an approximate value. So when does that new line cross the x-axis or the t-axis? Well, at about 5, right? So at about 5 years, the value would be $0. Okay, so the more careful you draw that line, which obviously I'm struggling hard with here, the more accurate or the more easy it is to read and extrapolate those values. So to use a ruler if you can, or even if you use a different piece of paper or something to line it up, just so you can see on the textbook. Okay, part B, when was the computer worth approximately 200? So we look at 200. Okay, we're going to draw a line across and down, and I think in about 4 years, the value would be 200 after about 4 years. And then we're also going to skip part C here. Okay, so that is basically it. So the key ideas here are interpolation and extrapolation. So you can use a line to interpolate values between known values. So just like this, we have these values that they've graphed for us. We can sort of guess what the values represent by going between these dots that are already there for us. And then remember, the key here is you can only basically estimate to one place more than the scale they gave us. So here, let's actually do this one. If we look at this temperature change at 2.5 minutes, okay, it's between 3 and 4, so we have to say 3.5. Okay, you can't say like 3.6 or 3.8. You can only go one more, essentially, is the rule. Okay, same with this one. It might look like 5.4 or something, but it's got to be 5.5. Okay, and same idea. It doesn't really matter whether we're starting with a known value for x or a known value for y. You just continue that line up to where it intersects, and then wherever that is, draw it across. Same with when you start with y. Okay, and extrapolation is almost the same thing, but here you can see they've done a nice job extending the line. Usually you make it dotted or a different color or something just to indicate that you are extrapolating, you're guessing at that point, but it works the same. So after 3.5 years, you look here, so here's what I mean. Between 60 and 70, you have to just say 65. Okay, you can't say like 63. That's kind of just the way that this textbook does it in terms of estimating. Okay, so the more specific your graph is, the more specific you can estimate. But these ones basically just go between it. So same thing here. We started at 80, we go down. That one looks like it's exactly 5. Okay, and it should only be used when it's reasonable to have values beyond the graph. So for example, it wouldn't make much sense to extrapolate this graph until there was negative money, because you're not going to pay negative money for a computer, right? They're not going to pay you to take the computer. So it only makes sense to extrapolate above $0. Similarly, this one also doesn't make sense to extrapolate this way because you can't have negative years, right? It wouldn't, like, that's just not how it works. So just before you just go into kind of autopilot, just make sure it actually makes sense in the real world to be able to extrapolate. Okay, let's try one question right from the assignment. We'll do number 4 together. The graph shows a linear relation between distance and time. So let's say they measured a car, how far it drove in a certain amount of time. That's a pretty common science physics question. It says for part A, what is the approximate value of the d-coordinate when t is 5? So for part A, we're trying to find what's the distance when t is 5. Okay, in 5 hours. So we'll look here when t is 5 hours. We'll look up. We'll see that that's the point. We'll kind of go across as straight as possible. Again, I apologize. If you look at where exactly it touches that red line, though, I think it's about 15. I would say 15. So D is 15 kilometers. Okay, it's better to be a little too general than too specific. Okay, if you said 14, I could see why you'd say that. The answer in the back likely would be 15, but check it. Maybe I'm wrong. And again, if you're off by 1 or 2, don't get frustrated. That's is mainly just to estimate. Okay, so if you're using the back of the book to check your answers, be a little bit generous with yourself. Okay, part B. What is the approximate value of the t-coordinate when d equals 0? Use a different color here. So, sorry, d equals 20. So we'll go up here when d equals 20. We're going to draw that across. And then this should work out nicely for most of them. So that one is pretty obviously 7 hours. So when d equals 20, the t equals 7 hours. There we go. And on a question with extrapolation, you may have to just extend this even further and then do the same thing. All right, so let me know if you have any questions. That is basically it, just reading graphs. Take your time, like I said, don't be too hard on yourself if your estimates are a little bit off, but in general, just try and keep them as broad as possible. All right, good luck.